All right, so in this video, we're going to introduce a new type of concept here. I guess we're building off these DFAs, the deterministic finite automata. So we use these DFAs to recognize patterns and strings, but the limitation in them is that the only memory the DFA has is its current state, and there are only a finite many of these states, right? Uh, so as a result of that, the DFA cannot count without bound. Right? Okay, so this motivates a new model, one with theoretically has unlimited working memory. This one's called the Turing machine. So the Turing machine is some type of computation machine, and it has a finite set of states and a start state. Now, it changes states as it computes, right? But the difference here, unlike the DFA, the Turing machine has a tape, right? So you can kind of abstractly think about like this tape that's kind of divided into cells. All right, extending in both directions. So here, we kind of we can think of an arrow pointing to a particular cell. Now at each step, so it'll either connect, excuse me, in each cell it'll contain some kind of alphabet, right? A symbol from the alphabet or the blank symbol, right? So something from our alphabet, or here the blank symbol noted by this pound key here. All right. So at each step, it can read the current symbol, write a new symbol, maybe the same one, right? Move one cell left or right and change state. So the tape is infinite, but only finitely many cells are non-blank at any time, right? Now here, if we have the concept of this being an infinite memory, just think of it as incredibly large in both directions, right? And if you happen to get to the end of it, you can just add more memory at the end. Okay? The computation ends when the machine enters the special halt state, which we call H. Right? The contents of the tape at that point are the output. So one possibility is that the machine never halts. Right? Think of that like an infinite loop in a program here. So a Turing machine formally is defined as a four-tuple M, right? That takes defined by Q, Greek letter lambda, Q naught, and delta. All right. Where Q is defined as a finite set of states. And lambda is an alphabet that includes the blank symbol. And Q naught. Right. So this is part of Q, but this is the start state. And then our delta is the Q set without the halting state. along with something from lambda, right? So it takes in two inputs, right? An alphabet times the Q, one of our states, and then it maps it onto the lambda, which may include the halting state, right? The reason we delete the reason we don't include the halting state here, because at that point it stops. So we're not worried about it's not taken into account here. So we have the finite set of states along with alphabet, and then that gets mapped onto lambda L R times Q. So this is the transition function, right? So this is what's called right. So it writes a symbol, it moves either left or right, and then it enters a new state. All right, that's what the LR means. So delta Q, this is using, just think of it like function notation in terms of an instance of what it would look like. We would write delta lowercase q, lowercase sigma, and that is tau dr. Okay, so this is what it reads, right? The Q, it reads the Q. Excuse me. The state is Q, and this is what it reads, right? What is currently in the cell. And then after this is what is written in the cell. D is the direction, and R is the state, the next state. The halt state H has no transitions. Once it reaches H, the machine stops. So H, the halt state, has no transitions. And once it reached, the machine stops. All right. Now, if we compare with the DFA has 5 components. Turing Machine has 4. Right. The accepting states F are replaced by the halt state. Right. So there are no different accepting states. There's just a state where it just stops. All right. The transition function now includes an output symbol and a direction of motion. So there are 3 possible outcomes here. So the first outcome is that machine halts with a clean output string on the tape. All right, this is our desired outcome. Okay, whatever we want the clean output of string to be, this is the desired outcome. Outcome 2 is that the machine halts but the tape is in a configuration that does not count as valid output. All right, think of analogous here to our DFAs, right? A clean output, you can think of that in our DFAs where we have reached an accepting state, right? And then outcome 2, like it ends, but it's not, the string is rejected, right? So think of it analogous to that, right? Now, there is a third outcome here, right? The machine never halts. All right, so essentially it runs forever without entering state H. All right, and now this is for the DFA outcome 3 is not possible, right? The machine always terminates after reading all the input. For Turing machines, non-termination is a fundamental possibility, and it cannot always be predicted in advance. All right, so here again, the key upgrade from a DFA to a Turing machine is this read-write tape, both direction movement, and the possibility of not halting. Right? In the next video, we'll take a look at diagrams for Turing machines and tracer machines on some concrete inputs. Right? Now, I'll end this by taking a look here at a way to visualize our Turing machine. So here, this is the first example of the machine, first example machine given by Alan Turing in his 1936 paper. So this is what he kind of visualized. So what you'll see here as, well, I'll let it run here. You'll see the movement of it. It just moves to the right here, and it just has alternating ones and zeros with a space, a cell, a gap in the cells after it writes. Now the convention there is it's reserved to marking the cell. If you want to mark a particular instance of what's going on in the cell there. Okay, now in the next video we'll get into these transition diagrams, and we'll learn how to trace them, right, and create them, right? But this is what we're looking for, right? The transition diagrams, and you'll notice here they are a bit different, right? As you see here, direction, right? They're all going to the right. You could see here the kind of loop that is hitting into, right? Direction, what to put in the cell, and the next state here, okay?